Exploration of the Moon, Class 3. This is September 19th, 2018, and my name is Jim Head, planetary geoscientist at Brown University, together with David Kring, organizing the course. So before we introduce our speaker today, I just wanted to go ahead to one slide here and point out that we have an addition to our lecture series, which is on November 7th. NASA Administrator James Bridenstine will talk to us about future lunar exploration. We're very excited about this. At the present time, he's working on a specific title, but he learned of the course and was very excited to talk to us about future plans for the exploration of the moon. And we're anticipating an hour presentation, and also he's welcomed us to ask questions for the additional half hour as well. So this will be very exciting. Put that on your calendars for sure. So today's class is on the formation of the moon current scenarios. And the speaker today is extremely well qualified to do that. This is Robin Canup from the Southwest Research Institute, which she joined in 1998. She's Associate Vice President for the Boulder Office Planetary Science Directorate, Space Science and Engineering Division of SSERVI. Robin got her BS in Physics at Duke University and a PhD in Astrophysics, Planetary and Atmospheric Sciences at the University of Colorado. And Robin's work, of course, her main research areas are the origin of planets and satellites, and she utilizes analytical and numerical methods to describe the dynamical evolution of systems of circumplanetary or circumsolar material. She's a principal investigator on a number of different NASA programs and also on spacecraft missions. So she is, of course, featured earlier on in our early discussion of our transformative lunar science that we had on the first class. And as you know from that class, she is a very articulate speaker. So with no further ado, let me introduce Robin to speak on the history, the formation of the moon current scenarios. Robin?
Okay, thank you. So I'm going to bring up my PowerPoint and then attempt to share my screen. Thank you to Jim Head and Dave Kring for organizing this seminar course and for inviting me to speak. The origin of the moon has been one of my primary interests for many years. I find it particularly compelling for a couple of reasons. Of course, the moon is our companion and has been throughout Earth's history, and so understanding the origin of the moon tells us about our own planet's past. But more broadly, the moon is an object about which we'll likely always have a lot more information than other planetary objects in the inner solar system, save the Earth. And because of that, understanding the origin of the Earth and moon has the potential to really provide a cornerstone in our understanding of how terrestrial planets form. And hopefully with that, we can learn something more broadly relevant to understanding the formation of the other inner planets in our solar system and in exosystems as well. So if you could go to the next slide, please. I'm going to start by describing the basic constraints that we hope that any good model for the origin of the moon can account for, and tell you about the giant impact theory, which has been the leading model for lunar origin since the mid-1980s. I'll then talk about what's been called the canonical impact of a Mars-sized body with the Earth. This is the type of collision that in the mid-2000s we thought really offered a compelling explanation for the Earth-Moon system. But over time, particularly in the late 2000s, it began to be apparent that the canonical impact had some difficulties, in particular in explaining a growing number of detailed compositional similarities between the moon and the bulk silicate Earth. And this has inspired a true renaissance of lunar origin studies over the past decade that have proposed a variety of new and creative models to try to address these problems. And I'll describe some of the main classes of those new models that I've listed here below, and then I'll finish with some kind of high-level implications. So if we go to the next slide, perhaps the most basic compositional property of the moon that we know from its bulk density is that it is highly depleted in elemental iron. The moon has less than 10% of iron by mass, versus the Earth that has about 30% of its mass in iron. So we know from that observation alone that whatever process led to the formation of the moon somehow selected against iron that is typically found in the cores of terrestrial planets. Next slide, please. We know from the moon rocks that the moon itself is very ancient. This object dates back to 4.51 billion years ago, implying that the moon formed only 60 to 100 million years after the oldest known solids in our solar system. So this is a truly primordial object from which we can learn things about the origin of the solar system. Next slide, please. So one of the interesting things about the moon is that its orbit has changed over time in a way that's directly coupled to the rotational state of the Earth through tidal interaction between these bodies. So if you look at the top image on the left, the moon's gravity is slightly different on different portions of the Earth. It's strongest at the point of the Earth that's directly closest to the moon, weakest on the part of the Earth farthest from the moon. And if you compare the different force vectors shown in this top diagram to the average gravitational force at the center of the Earth and difference those, you get what's shown in diagram B, which is the differential tidal force. So essentially, the gravity of the moon tends to distort the figure of the Earth. It tends to flatten it along the Earth-Moon direction. And in particular, you see this most clearly in the oceans. So if the Earth's shape, in response to the moon's gravity, distorted instantaneously, it would form in alignment with the Earth-Moon distance, as you see in this image B. But actually, there's some dissipation in the Earth, and it takes some time for the Earth to assume this equilibrium tidal figure. And in that time, because the Earth's rotation is somewhat faster than the moon's angular orbital velocity around the Earth's shape rotates ahead slightly of the moon. And you can see that in the figure on the right. So what that means is that close tide on the near side of the Earth to the moon rotates somewhat ahead of the line connecting the center of the Earth and the moon. That means that the gravitational interaction between that tide and the moon leads to a positive torque on the moon's orbit. So with time, this tidal interaction causes the moon's orbit to gain angular momentum and to spiral outward. It gets that angular momentum from the Earth's spin, which causes the Earth to slow down over time. Now, the astute observer will note that there is, of course, a tide on the backside of the Earth also. It's actually behind the moon position, and therefore it exerts a negative torque on the moon. But because that tide is farther away from the moon, it's smaller in magnitude than the tide on the near side. So it's the effect of the near side tide that dominates. And over time, this interaction conserves total angular momentum, but it causes the moon's orbit to expand with time while the Earth's rotation slows down. You can go to the next slide, please. So from this, we know that while currently the Earth-Moon separation is about 60 Earth radii, and we have a 24-hour day, if we integrate back in time to when the moon was close to the Earth, it was orbiting an Earth that was rotating much more quickly, with only a 5-hour day for the current Earth-Moon system angular momentum. Next slide, please. So the giant impact theory was proposed in the mid-70s. So the idea here is that there was a collision between two planets at the end of planet formation. That ejecta from this collision went into orbit around the Earth, and it was from this orbiting material that the moon later accumulated. And the impact theory has long been the leading one for the origin of the moon because it does a very good job of explaining the basic system characteristics. As we'll see, if you have a collision of two planets that are differentiated into iron cores and silicate mantles, the material that goes into orbit around the final planet tends to be derived preferentially from the outer layers of the planet. So an impact can naturally explain why the moon has so little iron. An off-center big impact is also the most natural way to explain Earth's rapid initial spin, as implied by the current Earth-Moon system angular momentum. And finally, we think these types of events were typical during the final stages of terrestrial planet formation. So let me describe what I mean by that. You could go to the next slide, please. So we have a number of specific models for terrestrial planet formation that are being debated right now. There are ones that assume Jupiter and Saturn in their current orbits. There are some that consider Jupiter and Saturn in more circular orbits, or they consider the effect of the giant planets migrating while the planets form, perhaps a grand tack or a Nice-like model evolution. But across all these different types of models, a common theme is that the final stage of building the inner planets involves giant impacts among initially a distribution of, say, 20 or so initially Mars-sized planetary embryos. So if you look at the top plot, this is a simple artist conception. You start with these embryos in relatively circular coplanar orbits. Their mutual gravitational perturbations cause their orbits to become eccentric and overlap, which then leads to mutual collisions and a process of elimination until you're down to only a few stable planets. And if you look at the models, you find that the Earth analogs produced by these planet formation simulations typically undergo several giant impacts as they are forming. And these giant impacts occur in the tens of millions of years to 100 million year time frame, which is consistent with the age of the moon based on the dates of the lunar rocks. Next slide, please. So we want to know how to decide whether or not an impact model is viable and what type of collision it was, how big the impactor was, its speed, its angle. So to do this, we build computer simulations to model these giant impacts, and then we treat them as essentially a laboratory experiment to learn what the outcomes of these collisions would have been. Next slide. So the most commonly used method is known as smooth particle hydrodynamics, or SPH. So you're describing the colliding planets by a multitude, typically a million these days, individual particles, and you're tracking the evolution of each of these particles during the impact. Now each particle is either a silicate or an iron particle. Next slide, please. And at each time step in the simulation, it's a full hydrodynamic simulation. So at each time step, you're computing the change you're computing the force on the particles due to pressure, explicit self-gravity, and shock dissipation, in addition to how the energy of each particle is changing due to pressure, compressional heating, expansional cooling, and shock dissipation. And then each time step, you're calling an equation of state to update pressure and temperature as a function of density and the energy of the particle. So next slide, please. So this is a simulation of a canonical impact by a roughly Mars-sized body. So the upper right object is the Mars-sized impactor. So it's going to collide with the Earth. You'll see the impactor stretched out. A portion of the impactor will gravitationally recoalesce, and there'll be a secondary collision with the Earth. And then there'll be a dispersed disk, ultimately, around the Earth. And we're looking on the collision from above. So Ricky, if you could click on the animation, and that should work. Hopefully. Ah, beautiful. Thank you. Okay. So, so in this and the few more subsequent animations, the color is scaling with temperature. The total time simulated here, it looks like it's momentarily stuck, but is about 24 hours. So this is a roughly Mars-sized impactor at about a 45-degree impact angle, and we assume that the impactor looked like the Earth in terms of its iron composition. But by virtue of the fact that most of the impactor's core ends up merging with the Earth, you end up with a disk that has only a few percent iron by mass. So next slide, please. So we can see that more clearly when we look at the same animation where red is iron and yellow is the silicate mantle. Now, before you start it, let me just explain one thing, which is what you'll see is that secondary collision by a large clump from the impactor is primarily the iron core of the impactor. Okay, go ahead and restart it, please. There's the initial collision, and right here is where the inner clump you'll see forming. Seems like it's stuck again. There's that clump, and it undergoes that secondary collision with the Earth. So again, we end up forming a disk that has about 2 lunar masses in it, and it's largely iron-free. Next slide, please. So this simulation shows the impact in reverse. So here yellow is the material that ends up in the disk, so that's the stuff that the moon's made from. Yellow are the particles that end up in the Earth, and red are particles that escape. And when you look at this way, you can see where the material that ends up in the disk comes from. So if you could run that animation. Oops. Yep. Now, one of the general traits in these giant collisions is that a lot of the material that's placed into orbit gets into orbit by virtue of gravitational torque. Interactions either among the material in the distorted shape of the impactor or between the impactor material and the distorted shape of the Earth right after the collision. And because of that, in most giant impacts, most of the material that ends up in the disk came from the impacting object, and that turns out to be a key result. So it looks like this animation is now completely stuck. You try clicking it one more time. There we go. Yep, yep, go, 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 go. Okay. So here the yellow particles are the particles that end up in the disk, and you can see they come overwhelmingly from the object in the upper right. That's from the impacting object. Okay, go down once more. And this is, next slide, please. And so this is the same impact shown just in 3D, so you can get a sense of the distortion of the Earth. Go ahead and click on this, and let's see if we can get this to run smoothly. If not, we can skip it. Okay. You're vaporizing typically at least part of the silicate of the Earth and the disk material. So after the impact, the disk is a mixture of silicate melt. Now we're looking at the system in the plane of the disk and silicate vapor. And I apologize for the joltiness of the impact. Let's go to the next slide. So how does this disk of ejected debris evolve into the moon? Well, to form a moon massive enough, as massive as ours, which has about 1% of the Earth's mass, we know that the disk has to be massive too, and because of that, it'll be subject to clumping due to self-gravity. Now, exterior to the Roche limit for silicate, which is shown by the blue circle, and is at about 3 Earth radii from the Earth's center, exterior to that distance, the clumps are stable, and they can form and then collide to grow a moon. Inside the Roche limit, clumps get dispersed by the tidal force of the planet. And that's what forms these trailing spiral arms inside the Roche limit that you see on this image here. This process of clumps forming and being disrupted creates a lot of energy, dissipates a lot of energy, it keeps the inner disk hot, and it also is a mechanism that causes the inner disk inside the Roche limit to spread radially, both onto the planet and out past the Roche limit. So next slide, please. So a simple model for this system and how the moon forms has been developed by Julian Salmon and myself. We consider an inner disk that we treat analytically as a disk that's spreading due to this clumping process. We treat the material outside the Roche limit with an N-body simulation, which we use to track the accretion of the moon. And the moons, as they form, interact with the inner disk. And the nature of that interaction is such that it tends to cause the orbits of the outer moons to expand outward. And if the interactions are strong enough between the outer moonlets and the inner disk, the moons will actually confine the outer edge of that inner disk. They'll push it inwards for a time. Our model also includes the spreading of the inner disk, and as material spreads outside the Roche limit, we add new n-body particles to our simulation of the moon forming. So if you could go to the next simulation, the next time step, please. So now we're looking at the system on edge, so that dashed line is the Roche limit. We're tracking the accretion of the moons in the outer disk, those are the black circles, and we're showing the radial extent of the inner disk by that orange bar. Let's try to get this animation to run. So you're going to click on that, you should click on here. And what we see is that very rapidly, in less than a year, the material in the outer disk accumulates into a single moon. And initially, it confines the inner disk inward, but eventually the inner disk spreads, and the inner disk material is the last material accreted onto the moon. And that's indicated by this growing orange layer that you see indicated on this diagram. Eventually, the moon's accretion of this inner disk material is cut off and its orbit expands outward. So in all, after 100 years or so, we're typically left with a single moon. Okay, next slide, please. So to sort of summarize, the canonical impact, this impact by a Mars-sized body with the Earth, explains many traits of the system very well. It gives you the masses of the Earth and Moon. It naturally accounts for the Moon's iron depletion. It gives you the Earth-Moon system angular momentum we see today. We know from our planet simulations, or at least we think from our planet simulations, that these Mars-sized low-velocity impactors were very common in the late stages of forming planets. Perhaps tens of % of Earth analogs in the models undergo an impact like this. And our models of how that disk accretes into a moon suggest that we form a single moon within about 100 years. So if this were like most astrophysical problems, where we're just observing a system from afar, we would look at the canonical impact and this list of success and conclude that we've found the right answer and that we're done. And this is where the problem becomes so interesting, because in the case of the moon, we're not limited to observing the system from afar. We have the samples from Apollo. And it turns out that those completely affect our understanding of the origin of this system. And in fact, the rest of the talk will involve issues that we only are aware of because of the fact that we have those Apollo samples. Okay, next slide, please. So what turns out to be the key issue that is challenging to explain in a giant impact model are a large number of compositional similarities between the moon and the Earth's mantle. And these are similarities in the isotopic composition of what we now know are multiple elements. Now, in general, we knew about some of these similarities as soon as we saw the Apollo samples, as soon as we got them back. But what's happened over time, excuse me, is that the precision of the measurements has improved. And so while initially there was enough uncertainty to permit modest differences between the Earth and Moon, with time the measurements have become more precise, and as they become more precise, it's looked more and more like the Earth and Moon are essentially identical. In addition, we found that these isotopic similarities between the Earth and Moon extend not just to oxygen, which I'll use as a key example, but to multiple other elements as well. So let me talk about oxygen. So there are 3 stable isotopes of oxygen. Most oxygen atoms are O16, but a small percentage have 1 extra neutron, O17, and an even smaller percentage have 2 extra neutrons, O18. And so by isotopic composition, what I mean is that you're looking at the fraction of, say, O17 compared to O16 in a sample, compared to a reference sample. And these are very small differences. So in this case, you're looking at those in parts per thousand. Now, if you look at a sample of ocean water from the Earth and look at the ratio of O17 to O16 and O18 to O16, and you look instead at a sample from a cloud on the Earth, those 2 samples will have different ratios. In other words, they'll fall at different places on this plot. And that's because processes like evaporation and condensation will change the relative fraction of O17 and O18 versus O16 in a given sample. But those planetary processes change the isotopic ratios in predictable ways, and that's because they work in proportion to the mass of an isotope. So what that means is if you see a sample and it has a relative deficit in O17 of some amount, then that same sample will have twice that magnitude of deficit in O18. And that's because the mass difference between O18 and O16 is twice the mass difference between O17 and O16. The end result being, when you plot the terrestrial values from any terrestrial sample on a plot like shown here, they fall in a single line, the terrestrial fractionation line, the line in the lower right. Now, if you do the same analysis for meteorites from Mars, you see that they all lie on a different line that is about 300, offset by about 300 ppm from the terrestrial fractionation line. And that's a big difference. That's easily observable. So the interesting thing is that when you plot the moon values on top of the terrestrial line, they fall right on the same line. And over time, the degree to which they fall on the same line has gotten, much more confined. So we now think that the moon and the Earth are identical to within about 10 ppm in terms of lying on the same fractionation line in oxygen. So let's say Mars is the only other planetary body whose isotopic composition we know. All right. So if we say that the moon-forming impactor could have been as different from the Earth as Mars, or even somewhat more similar, but still different, can you give me the next slide, please? Then we have a problem with the canonical model. Can I have the next slide, please? And that's because in the canonical model, the disk forms primarily from the impactor. And so if the impactor was different in composition from the Earth, then the moon that formed from that disk should look different from the Earth, and yet it looks the same. And so here's a color representation of the differences between the impactor and the target compositions. And after a canonical impact, you form the disk. It's about 80% from the target, 80% from the impactor and 20% from the target. Whereas the planet comes mostly from the target, with just a little bit added from the impactor. So if you, after the impact, compare the relative compositions of the disk and the planet, they're very different. 20% target versus 90% target. And if we wanted to explain that oxygen isotope similarity in the case where the impactor was Mars-like in its isotopic composition, you would need these two percentages to be the same to within a few percent, and instead they're different by 70%. So that's the fundamental problem with the canonical impact. Next slide, please. So the first solution, possible solution, is that maybe we were lucky in the sense that maybe the impactor that formed the moon just happened to have been much more Earth-like than Mars. So one way of quantifying this is to imagine that there might have been a distribution of oxygen composition in the solar nebula when the planets formed. And if we set the radial distribution so that we get Mars and Earth at their current values, then we can ask how likely was it that the impactor formed close enough to the Earth that it would have been Earth-like in its composition. And a number of works have done such an analysis. And the take-home is that most impacts usually involve objects that are compositionally distinct. But in some 5 to 10% of cases, you can find the final impact the final impactor being very similar in composition to its target. Okay, so that's one possible solution that's been proposed. Next slide, please. So the next idea that was proposed is a concept known as equilibration. So the idea here is that you had an impacting planet that was different in composition from the Earth. So initially, the disk had a very different composition from the Earth, too. But then right after the impact, because remember, a substantial portion of the planet and the disk are vaporized by the impact. So in the aftermath of the impact, if you imagine that there was diffusive mixing between the disk and the planet due to convection, for example, this could have equilibrated their compositions after the impact, but before the moon formed. So if you do estimates for how long this equilibration process would take, it would take about 100 years. And based on the types of models I showed you before, that looks plausible for the lifetime of the inner disk. But the models we've done, as well as the more recent models by Locke et al., suggest that the outer part of the disk will accumulate into the moon quite rapidly, in less than a year. And so one possible idea is that maybe the initial portion of the moon, shown here in blue, that reflects the outer disk material, might not have equilibrated the Earth, but perhaps the last portion of the disk that accreted onto the Earth, that came from the region near the Earth, might have been more likely to equilibrate. Another possible test of this equilibration idea is if you imagine a disk structure like is shown in this diagram, where there's a midplane of melt and it's surrounded by an atmosphere of vapor, and it's the vapor that's mixing, then you might expect that the equilibration could be less effective for highly refractory elements that are concentrated in that melt phase. And so you might expect to see, if equilibration was responsible for the Earth-Moon similarity in oxygen, that the Earth-Moon might be different in highly refractory elements. And at least today, if you look at titanium, at least based on data obtained to date, if you look at titanium, the Earth and the Moon look identical. And based on very recent work, they may have a very small difference in calcium. So equilibration remains a very attractive way for explaining Earth-Moon isotopic similarities, but exactly how it works and how probable a mechanism it would be remains unclear. Next slide, please. So a third type of solution was proposed in 2012. Now, we looked at the tidal interaction between the Earth and the Moon, and I mentioned that that interaction conserves angular momentum. And so until 2012, we thought that a viable moon-forming impact would have to leave the Earth-Moon system with an angular momentum to say within 10% of the current system value. But in 2012, Shook and Stewart identified a mechanism that can remove angular momentum after the moon-forming impact. And I'll describe that in a bit more detail in a moment or so. Because of that, we broadened our consideration of impacts to those that would leave much more rapidly spinning planets with a lot more angular momentum than is currently in the Earth-Moon system. And it turns out, among high angular momentum impacts, there are actually two limiting cases that can produce a planet and a disk with equal compositions. And those two different cases are shown here. The one on the left is known as the fast spinning Earth impact, and the one on the right is known as the half-Earth impact. Next slide, please. So in the fast spinning Earth impact, as its name implies, before the moon-forming impact, the Earth is spinning very rapidly at near the rotational instability rate. The moon-forming impactor is relatively small and high velocity, and the material placed into orbit as a result of this is derived overwhelmingly from the target. And you see that in the pie for the disk on the right, showing that the disk is often comprised of 92% target material. So essentially, you can think of this model as an impact-induced fission, in effect. Next slide, please. So an alternate way to get a disk and planet that have very similar mixtures of target and impactor material is to imagine a nearly symmetric impact. Now, in the limit that the impact was completely symmetric, and by that I mean two exactly equal objects in mass colliding together, you would, by symmetry, form ultimately a planet that was derived half from the impactor and half from the target, and a disk that was derived half from the impactor and half from the target. Now, you would never actually get a perfectly symmetric impact. That would be extremely improbable. But it turns out that even if the impact is somewhat less than symmetric, as you can see on the right, you end up with a disk and a planet that have very similar mixtures of impactor and target material. So both of these impacts are uniquely, perhaps, among impacts, able to produce a disk and a planet that have the same composition. And yet both of them leave an Earth-Moon system with about twice the angular momentum that we currently have. Next slide, please. So both of these require a mechanism to remove that angular momentum after the moon-forming impact. So one such mechanism is the Evention Resonance. So this is a resonance that involves the sun. The moon's orbit is slightly elliptical, it's not circular. And the moon's orbit precesses over time due to the non-sphericity of the Earth, due to the Earth's oblateness, is J2. And that precession period is a sensitive function of distance, so as the moon tidally evolves outward, that precession period changes. And the Evention resonance occurs when that precession period is exactly 1 year, so it's commensurate with the Earth's orbit around the sun. Now, when that occurs, the moon's orbit is maintaining a fixed alignment as the Earth orbits the sun. And in the Evention resonance, it will align itself either to oscillate around the positive x-axis, as shown in the top of the diagram here, or have its periapse aligned on the other side. Both of those are stable points. So now, in the absence of any tidal evolution, the sun will cause the moon's orbit to lock around this alignment and to oscillate, but there won't be a net transfer of angular momentum. But if you have the moon tidally evolving as well, then there can be a net transfer of angular momentum from the Earth-Moon system to the Earth's orbit around the sun. This was known previously by work by Tuma and Wisdom, but earlier work suggested that the change in the angular momentum of the Earth-Moon system would be small, of order less than 10%. But Shook and Stewart in 2012 had a big breakthrough in that they showed that for certain tidal parameters, the angular momentum transfer could be very large. You could remove, you could change the Earth-Moon system angular momentum by a factor of 2 or more. Next slide. So this has been very exciting to those of us in the dynamics community. Lots of people have started doing follow-on work on this. And the constraint that has emerged to date is that you seem to go from a very high angular momentum system to a system that's consistent with the Earth-Moon angular momentum over a relatively narrow range of tidal parameters for the Earth-Moon system. When other works that have investigated what those tidal parameters might be suggest that a broad range of parameters might be plausible. And so, at least right now, we're not sure of how likely it would be to find the system with the right tidal parameters to give us the angular momentum we want from this mechanism. There's also been another mechanism that Shook et al. Have proposed in 2016. This involves the sun. It's another type of mechanism. And it's not clear yet over which range of values it operates best over. Next slide, please. So at least for the single impact models, we sort of have two limiting classes, I would say. So in this plot, on the y-axis is the Earth disk compositional difference, and the x-axis is showing the system angular momentum scaled to the current angular momentum of the Earth-Moon system. So the points, the circles and squares and the triangles, those are results from SPH impact simulations. And if we imagined that the impactor was compositionally different than the Earth, then we would want these points for agreement with the Earth-Moon system to fall within that box that contains the hatched lines on the lower left. And so within that box, you have a disk and planet similar enough that they would give you the Earth and Moon oxygen similarity, for example, and you would leave a system with an angular momentum consistent with the current angular momentum. So we have two classes of impacts. The circles up top, those are the canonical cases. They give us the right angular momentum, but they have this big compositional difference between the Earth and the Moon, so it looks like if the impactor was different from the Earth, we would need something like equilibration to remove that compositional difference. On the other hand, the high momentum impacts, those are the triangles and squares, they're giving us very similar disk and planets in terms of their composition. So we're getting the composition match right for those. But their angular momentum is much larger than that in the current system. So we need a mechanism like the Evention Resonance to pull us to the left in this plot to bring us back into the box. Now, there also, if you consider that after the impact, you might have both angular momentum removal or transfer to the Earth's orbit and equilibration, then there are intermediate cases that fall in between these cases as well that are being investigated right now. So the take-home message from this is that at least from single impacts, if we assume the planet was, or the impacting planet was non-Earth-like in composition, then we don't have any points that fall within that box directly. All of our current single impact scenarios, if you assume the impacting planet was compositionally distinct, require some secondary process to get us back to the Earth-Moon system. Next slide, please. Which brings me to the most recent new proposal for a moon origin idea. Can you give me the next slide, please, Ricky? And that is a great out-of-the-box idea, which is to put aside the assumption that the moon was formed by a single impact and instead consider that it could have been the cumulative result of many impacts. So here the idea is that you have a lot of sub-Mars-sized impacts, and each one creates a moon, which then tidally evolves. And then the next impact creates a secondary moon, and those two moons merge. And in this way, through sequential impacts, you build up the moon. So why is this advantageous? It's advantageous because as you make the moon through a larger number of impacts, the compositional difference you end up with between the final Earth and moon is decreased. Maybe impact number 1 was different in this way from the Earth. Impact number 2 was different in a different way. The difference between the final planet and disk tends to average out. And the work by Rufu et al., 2017, shows that if you form the moon in this way through about 20 impacts, you can form a lunar-sized moon if you assume that all of the moons produced by sequential impacts merge, and that in a substantial number of cases, the Earth and moon are compositionally similar. So those are good successes. The issues are that it's not clear the extent to which moons formed by different impacts would necessarily merge with each other, or whether you might tend to lose a prior moon to impact with the Earth or to escape from the system. And another issue is that if the moon is present alongside the Earth for a long time, as the Earth itself is growing, then the moon may be vulnerable to accreting too much iron-rich material from heliocentric impactors. And we know that we have a strong constraint on the total amount of iron that can be accreted by the moon. Next slide, please. So where are we at? So explaining these detailed compositional similarities between the moon and the Earth's mantle has proved to be extremely challenging. Over time, the numbers of these similarities has been increasing. And indeed, as I mentioned, if you assume that the impactor was in any way as different from the Earth as Mars is, then all of our single impact solutions seem to require some additional step to modify the system after the impact to bring us into agreement with the current Earth and moon. So you either need something like equilibration to erase the compositional differences between the disk and the planet, or you need a mechanism like the Evention Resonance to remove angular momentum after the impact, or maybe you need both. And many of us think that given these types of constraints, we need to be carefully considering whether or not we're missing something, or perhaps the better way to put it is that we could be misinterpreting something. And something that a lot of people are questioning right now is this idea that the difference in compositions between Earth and Mars is really telling us or is really reflective of the compositional differences of the late material accreting onto the Earth. If it wasn't, for example, if the inner solar system where the Earth was accreting was much more isotopically uniform, then a lot of the constraints I've talked about are eased, and we would have more natural explanations. So a key piece of data that we lack right now is the isotopic composition of Venus. So, for example, if we were to know the oxygen isotopic composition of Venus, and it were to be similar to the terrestrial fractionation line, then that would be a strong piece of evidence in favor of a relatively uniform isotopic population of material in the inner solar system. Now, that's a very challenging thing to obtain, but some very clever and insightful analyses of just the composition of the Earth in different elements that reflect different stages of its accretion by Nicholas Delfas has begun to place strong constraints on how Earth-like the last half of Earth's mass that it accreted was. And to date, those analyses suggest that the late material accreted to the Earth did isotopically look much more like Earth than Mars. And on the next slide, and that's my last one, I just have a list of things to prompt discussion, which are a handful of observations and future models that could really help provide additional constraints on this problem. And Ricky, could you, I should have one more slide, I think. Can you click to that one for me? Yeah. There we go. So one, of course, is Venus's composition. Points 2 through 4 here are issues that I think there's truly the potential to have fundamentally new information associated with a near-term expansion of lunar exploration. These range from better knowledge of the composition of the moon, whether or not it is compositionally homogeneous or heterogeneous, and its initial volatile content, constraints on the degree to which the moon was initially molten, whether it was fully molten or partially molten. This turns out to be a very important constraint for the models, because the portion of the moon that forms in less than a year will by necessity be initially fully molten, and having an only partially molten moon with an outer magma ocean may prove to be a strong constraint on the disk conditions. The ages of the lunar impact basins are a key importance to lunar exploration. And we often think about those in terms of just better understanding the flux of impactors in the inner solar system. But they also provide a key constraint on our models of terrestrial planet formation. And I think that as we learn more about those basins, we'll be able to improve those models and our estimates of the degree of radial mixing as these giant impacts were occurring. This gets again to the issue of how Earth-like compositionally was the moon-forming impactor. And then point 5 is addressing the fact that we think that Earth-like planets would have undergone multiple giant impacts. And now that we understand that many impacts produce moons of different masses and compositions, it's natural to ask, does our moon predominantly reflect a single impact, or could it be the result of more than one impact? And that's something that we need better models on how multiple moons evolve and how the rotation state of planets evolves as they undergo these giant impacts. So I'll stop there. Thanks, and thank you for your patience with our technical difficulties.
Thank you, Robin. You hold up very well under pressure there. It was excellent. So I had just a couple of questions to start, and then we have a number of others as well. So under what we understand now, what is the latest, how long can a second moon survive in Earth orbit? Does anybody have a theoretical or model idea, based idea on that?
So if you imagine a second moon that was produced by an impact, okay, then you then it comes down to a, if you have a typical time between impacts of, say, 10 million years, and your moon number 1 tidally evolved outward before moon number 2 is formed, then a typical separation between them in terms of their semi-major axes might be of order 10 Earth radii. So the inner moon, especially if it's comparable or somewhat higher in mass, will tend to overtake the outer moon as it tidally evolves. So each system is different. You can get very rapid collision times for some situations, but in general, the reaccretion time between the two moons tends to be much shorter than the time between subsequent big impacts. So generally, in for example, 1 million years, you've probably had a collision between those two moons, or had one hit the Earth.
Okay. So another question I had was a very general one. I was thinking before the advent of the giant impact hypothesis at the meeting in Hawaii, I wondered, so there was a series of hypotheses there, and I wonder, reflecting back on those hypotheses, could one option be that the giant impact isn't the answer, and one of those now, maybe needs to be reconsidered, or pretty much have they been ruled out?
Well, I think the answer to your question is both yes and yes. So let me clarify. So the basic theories included intact capture. So the moon forms as a separate object that is captured into orbit around the Earth. Co-accretion, which is as the Earth grows, it has a disk around it, and the moon grows alongside the Earth. Fission, where you have a planet that rotates at the instability rate, and it becomes unstable, and the moon forms from the ejected material. And giant impact. Okay. Now, among those, I would say that capture is still viewed as extraordinarily unlikely in a couple ways. First, it's very difficult to go from an unbound orbit to a bound orbit during a single pass to find a source of energy dissipation. And capture would require the moon to have formed with its very unusual iron content and then be captured intact. And that's seen as very improbable. Now, the other two ideas from that Kona meeting, other than the impact theory, were fission and co-accretion. And indeed, the Chicken-Stewart model, the Chicken-Stewart 2012 model, is, as I mentioned, very akin to the fission model, because you basically have the Earth rotating at a near fission rate, and you hit it with a smaller impactor, and then the material in the disk comes from the Earth. So we really are considering a variant of the fission model now. It's just an impact-induced fission. And similarly, you can view in some respect the multiple impact model as being akin in some respects to a co-accretion model, right? Because yes, you're producing disks from impacts, but you're producing the disk from many impacts, 20 or more. And so you really have the moon growing alongside the Earth. So I would say, in a way, the field has sort of broadened its thinking to include, in some senses, both the fission and the co-accretion model, but in the context of what we think was this large impact-dominated phase of terrestrial planet formation. So yes, those are the types of things we are questioning and re-examining.
Thank you. Let me turn it over to Ariel Deutsch now, who has a collation of some of the additional questions.
Hey, Robin, we have some questions starting out with thinking about the composition and isotopic constraints. So the first one is asking about how you mentioned that isotopes from lunar samples compared to bulk Earth composition, and we have a question about how isotopes from lunar samples might compare to deep Earth, specifically thinking about samples perhaps from large, low shear velocity provinces.
Right. So, so one of the things we attempt to do is we attempt to use samples of both the moon and the Earth to deduce a bulk composition of the silicate Earth and a bulk composition of the silicate Moon. Now, in both cases, that is not a trivial thing to do because, for example, in the case of the Moon, we lack samples of the Moon's mantle. And the Earth has undergone processing as it formed. And so we're inferring a bulk composition from a number of different source regions. Now, an interesting thing when it comes to the Earth's inferred isotopic composition is that it is not completely uniform. And one of the recent sets of constraints that's very interesting is that there seems to be, in some ancient regions, differences in what we see in terrestrial rocks from those regions versus what we see from most terrestrial rocks. And this, for example, occurs in the isotopes of tungsten. And so the interpretation is that the Earth's mantle was actually not fully mixed or homogenized after the Moon forming impact. Because if it was, these isotopic inhomogeneities would not have been preserved. So one set of constraints on the Moon forming impact that has been considered, which I didn't talk about, is, do we need to imagine a Moon forming impact that did not fully mix the Earth in order to preserve such inhomogeneities as those that we see? And I would say the answer to that question right now is mixed. There are definitely impacts. The canonical impact does not appear likely to fully mix the Earth. The higher momentum impacts tend to, but with that said, even those impacts may leave a deep portion of the Earth's mantle not fully mixed. So, these are very interesting questions, but in general, these inhomogeneities that we see in some Earth rocks may themselves reflect only a very small portion of the Earth's mantle, perhaps only a few percent. And so that's one of the challenges in trying to use a lack of complete mixing of the Earth's mantle as a strong constraint on the lunar origin models. So hopefully that covered the area around this question.
Great, thank you. We also have a second question that was submitted about oxygen isotopes. So we only have measurements for Earth, Moon, Mars, and asteroids. And we have a question asking whether the values of the Earth-Moon system being more difficult to achieve because Mars and asteroids are different, is it possible that Mars and asteroids have isotopes that are more outliers? So in other words, could the Earth-Moon composition be the normal?
Absolutely. And actually, that was the point I was trying, perhaps not clearly enough, make on my second to last slide, that one of the interpretations that many people in the field are questioning right now is the idea that when we look at Mars and meteorites, that their difference in, say, oxygen isotopic composition from the Earth is telling us something about how different the Moon forming impact would have been from the Earth. Maybe it's not at all. Maybe those reflect a very different region, very different processes. And indeed, when in Dauphin's 2017, when he takes a different approach to look at the isotopic composition of the last, say, 40% of Earth's mass, he sees that it looks indistinguishable from a very particular type of meteorite known as enstatite chondrites that is quite Earth-like in its isotopic composition across many elements. So I would say a lot of us think that we are possibly being misled by only having Mars and the meteorites to guide us. And again, Venus would be a vastly stronger data point for the simple reason that it's so much bigger in terms of its total mass. It's similar in mass to the Earth versus Mars, and of course, all the parent bodies of meteorites represents a much smaller total mass.
Thank you. We have another question about the composition. So our question is whether or how does the presence of water in the lunar interior influence formation models, given that the moon is relatively depleted in other elements that are easily vaporized?
Yeah. So, a fascinating story. How to explain the relative volatile content in the moon versus the Earth. Initially, when the giant impact idea was first proposed, it seemed to be generally a good thing that this would be a very high energy event, and therefore you might expect the moon that formed from this impact heated material to naturally be depleted in, say, the moderate volatiles compared to the Earth, because indeed the lunar rocks looked dry in elements like potassium, sodium. But as people have developed models of this process, it's clear that even though this material after the impact is vaporized, and so the volatiles will be overwhelmingly vaporized after the impact, those volatiles don't easily escape the Earth-Moon system, just due to the thermal velocity, the relevant thermal velocity of the vaporized species being low compared to the local escape velocity from the Earth. And so we think actually now that the post-impact system was closed, that Nakajima and Stevenson have recently published a paper looking at even hydrogen, which by virtue of being light is the easiest element to escape, and yet even hydrogen doesn't efficiently escape. So we now think that after the moon forming impact, the volatile elements will not escape. They'll be vaporized, but they'll still be bound to the system. So then they start to condense, and the question is, where do they go? Do they end up in the moon? Do they end up accreted by the Earth? In the case of water, do they end up getting dissolved in the magma under pressure? And can that explain the presence of water that is now known to exist in some of these lunar samples? So as you can probably imagine, the answers to those questions does depend on the disk evolution model and perhaps even on the initial state of the disk, which can vary from these impact models. So in general, I think that a better understanding of the volatile content of the moon, and in particular, if it varies with depth, will be key to helping to ultimately distinguish among these different models and perhaps disk evolution histories. But the takeaway is, it doesn't look like having water in the moon is inconsistent with an impact origin. That material, even hydrogen, is probably not going to efficiently escape after the impact. Water vapor certainly will be bound to the system, and that water could be dissolved within the magma in the disk. The open question being, what fraction of the moon was volatile rich, and does that, is that easily explained by the type of argument I just described? And we don't have an answer for that yet.
Cool, thank you. We also have a few questions related to the impact scenarios you discussed. So the first is related to the scenario where you talked about it's possible that there are many impacts that have occurred over time to produce the moon. And the question is, if the moon was impacted by over 20 large impactors or so, what is the probability that other terrestrial planets would not have experienced this extensive bombardment to form their own similar moon?
So this is a very good point. Even if you're not thinking about the multiple moon model, even if you're just thinking about the single impact model, then it is a very good question to ask. Now that we think the terrestrial planets grew through these giant impacts, and now that we know that most impacts produce moons, why don't we see moons around other planets? So that's a good question all around. So we actually have a series of papers, including one by Julian Salmon and myself this past spring, that argue that Phobos and Deimos may actually be the last remnants of an impact-produced disk around Mars. So there is now a set of models for the origin of Mars's moon that are related to a single impact with that planet. With Venus and Mercury, it seems, at least to me, that the likelihood that you had a Venus without ever having moons is very small. I mean, we think that to grow a Venus-sized planet, you probably had multiple large impacts. Venus probably did have moons. So the natural thing to conclude is that it had moons that eventually tidally decayed or were lost. There's been an idea proposed by Pallavan and Morbidelli that they have looked at the effects of large planetesimals in the inner solar system, not undergoing direct collisions, but just undergoing near passes. And these can gravitationally perturb the orbit of a moon. And they looked at this effect specifically to explain the origin of the moon's orbital inclination. But at the end of the paper, they also mentioned that if you imagine earlier formed moons, when this background population of large planetesimals was larger, then these near misses may have actually dislodged many prior moons. And that may be the reason why we don't see a moon around Venus today. So these are good questions, and we don't have solid answers, and answering this question with specific models is difficult because describing the lack of something often doesn't have as many constraints as trying to describe the presence of something with known properties.
So again, thinking about that multiple impact scenario, is there a threshold that a certain percentage of the impactors have to be Earth-like in composition?
No, and what they did, they assumed an initial radial gradient in the nebula compositionally that's consistent with the Earth-Mars difference. All right, and then they selected sources of the impactors with general statistics consistent with n-body planet formation models. So in their model, they were starting with a distribution of impactors that were compositionally distinct. They did not impose an Earth-like composition on their impacting population. But they end up getting an Earth and Moon that have similar compositions by virtue of having sort of multiple impactors, some of which have whose changes in composition kind of cancel each other out to some effect, to some degree, if that makes sense.
Thanks. And then also about the scenario regarding the fast spinning Earth.
Mm-hmm.
Can you clarify why the Earth would have started out spinning so quickly, and if other planets may have been approaching a near instability rate early on?
So the idea would be that near instability rotation before the moon forming impact was due to earlier big impacts on the Earth. Okay? And whether or not that would take a single really big impact on the Earth right before the moon forming one, or whether it could be the cumulative result of a couple big impacts, is still being debated. But that's the imagined source of that fast spin rate.
Thanks. And then with the last few minutes, we had a couple of questions regarding the models and the simulations that you run. So the first is asking whether the Earth-Moon system is tracked as a closed system, or if there's exchange with other smaller impactors and lost to space.
So when we do the impact simulations of the collision, the SPH simulations, we're just looking at two bodies. There is no other, there's no other entity in the simulation. So we do distinguish between material that is bound to the post-impact planet versus on escaping trajectories. And we essentially do the same thing in the simulations of the moon's assembly from the disk. In other words, we can, because those are n-body models, we can tell whether material is escaping from the Earth, but those models, at least to date, haven't explicitly had the sun in them, for example, or other third bodies.
Would you be able to talk a little bit about the initial thermal states that start your simulation?
Sure. this is something that we don't know well, but turns out fortuitously not to have a big impact, or effect, I should say, on the impact simulation outcomes. So in general, we know that if a planet is fully molten, prone to efficient convective cooling, which tends to make it start to solidify. But then as it starts to solidify, the degree to which it can cool by convection, the convective motions become more sluggish, and the degree to which the planet can efficiently cool decreases. So therefore, if you're really molten, you cool quickly, but then as you start to solidify, your cooling efficiency drops, and then you tend to more easily heat up, say by later impacts. Because of those kind of basic arguments, we think that the typical state you'd find the interior of one of these planets in the late stages of accretion would be near the solidus. Okay. Now, you know, there is uncertainty there, and one of the parameters that's varied across the simulations is the in some cases is the initial assumed thermal profile in the Earth's interior, and at least in the studies of which I'm aware, it doesn't end up making a substantial difference in the overall outcome of the impact, largely because it's typically the energy of the impact that is much larger than the differences in thermal energy in the Earth's pre-impact interior state.
Thanks. And then lastly, we have a couple of geochemists in the class. So we have a question on trying to understand the different geochemical constraints in moon-forming equilibration models, besides silicate iron mass transfer. So for example, they're interested in whether it's possible to track element-specific diffusivities or partition coefficients for various pressure and oxygen fugacity conditions.
So this is in the context of the equilibration model, right? Did I understand that correctly? So in other words, if you imagine that this convective-based mixing was taking place, then could you make specific predictions about Earth-Moon similarities from element to element based on different proportions in the melt versus the vapor as a function of oxygen fugacity, and that?
Right, exactly.
Okay. So essentially the types of, the analysis today has been simpler than that, and I'll explain why. Essentially, if you calculate, it's thought that the rate limiting step in the equilibration process, there's lots of different states, rates. You know, there's a vertical mixing rate in the disk between the melt and the vapor, or maybe if the melt is within the vapor exchange. But among these different rates, the one that's thought to be the rate limiting one is the radial mixing in the disk. Okay, so what's typically done is to look at the predicted time scale for a given element to be diffusively equilibrated between the Earth and the Moon. So from some initial difference, say, if you assume a Mars-like initial composition, for example, and say, well, for that element's volatility in the expected disk conditions, how long would it take to equilibrate those compositions? And the estimate you get on how long that will take depends on things like the volatility of the individual element. So, for example, oxygen will tend to be mixed perhaps on a shorter time scale than something like zinc. But when you calculate this quantity, I'm sorry, not zinc, titanium, I misspoke. But when you calculate this quantity for a given element, what's been done to date is just to compare that to the overall time scale for mixing in the disk. And then you say, let's take titanium, for example. As I mentioned, it's a highly refractory element, and the titanium compositions of the Earth and the Moon look the same. So does that rule out equilibration? And the answer is no, it doesn't, because for viable disk conditions, you would expect that if you had about 10 years, if you had about a decade, you might be able to equilibrate the titanium compositions. And the disk may last for 100 years. So to try to explain that a little more clearly, to date, we just have arguments that say, essentially, for every element that we estimate it could equilibrate on a time scale shorter than the disk lifetime, we think all of those could plausibly equilibrate. Now, when you get to an element like calcium, super refractory, then the equilibration timescale estimates start to be longer than the disk, comparable to or longer than the disk lifetime. And so that's why there's a lot of interest right now in whether or not there is a difference in calcium isotopic composition between the Earth and Moon. And the latest results from this year look like there is a difference, but it's really small, of order 10 ppm.
Thank you very much, Robin. We really appreciate your efforts here and also the really excellent answers to the questions. So now that Robin has created the moon for us, we're going to move next week on September 26th. The title of the lecture and discussion will be Formation of the Lunar Crust and the Aftermath, the Magma Ocean Hypotheses, and it'll be presented by Mark Parmentier from Brown University. And we will indeed have the readings up tomorrow afternoon on this on our website, and a reminder that also the lectures are being recorded and you can play them back at future times. That'll be also on the website, and it's already on the SSERVI home site. So I just wanted to remind you one more time to thank Ricky Guest for all his technical help for sure, and remind you that on November 7th at this class, Jim Bridenstine, the NASA administrator, will be joining us to talk about future lunar exploration, and also will be answering questions in the same format we do in our normal classes. So we're all looking forward to that, and the number of other guests who will be talking about the moon in the interim. Thank you very much from David Kring and myself, and we look forward to seeing you next week. Thanks a lot, Robin.
Thank you.